talk is in some sense the continuation of my previous seminar. In the previous seminar, I discussed how we can model the data obtained with electroencephalography, EEG data. Now I will present another method, and not only the method, it will not be about modeling of the EEG data, but in some sense about treatment of the data, how we can study some of the properties of this data of spatial temporal dynamics. And what is also written here, optical flow pattern, is a method to study some data, and I will explain what it is about. So first of all, I will very briefly recall, I will not stop on that really today, what we are talking about, what is EEG. So there are some experiments. These experiments can be very different, or it can be some clinical data for diagnostic of patients. Anyway, there is EEG electrodes on the head. Each of these electrodes gives a curve like shown in this figure in the right. There are many such curves. For example, here there are 30 electrodes. Each of them gives such curve. So horizontal axis is time, and here on the vertical axis there are many curves. Each curve is the value of electric potential at this particular electrode on the scalp. Altogether, it gives such a picture, and here, as I say, there are 30 electrodes, but it can be much more, up to 256 now. And before, people used like 2, 3, 4 electrodes. So now it's a large range of different devices. And the results of this, after that, there are different ways to represent these results. The most common ones are shown here. For example, you see in this figure here, there are many curves. In fact, each curve corresponds to one electrode. So here there are 30 curves put together. This is time, and this is the value of the electric potential at each of these electrodes. And before I mentioned that very shortly in the previous seminar, when we have this raw data, from this raw data to this stage, there are many intermediate steps, treatment of the signal. I will not talk about this. Moreover, I'm not specialist in this question. But what we should know is that there are different ranges of frequencies. Standard ranges are delta, theta, alpha, and beta. So the signals then filtered according to this frequency. And here, I don't remember which frequency, probably alpha frequency we see here in this figure. And you see this curves, the behavior can be different as shown in this figure and in this figure or in this figure. I discussed this last time. Well, I will briefly return later in my today's talks, but this is not a point for today. And another way to represent the EEG data is shown in the color images. Sometimes they are called topographic maps. So it is the same data represented in a different way. So each of these electrodes we consider as a point on the scalp. So the small picture represents the scalp. Each of these electrodes is a point at the scalp. At each moment of time, we have 30 points at the scalp with the values of their signals, and then so we have this. Of course, the scalp is not a circle, but it is projected on a circle, and so we have 30 points in the circle at each moment of time, and then this function is interpolated on the whole circle, and this gives us the scalar the scalar image, which corresponds to the level lines to the level of these two-dimensional functions. This is the main idea. So finally, what we have here, again, we have, for example, in this left image, we have a two-dimensional function. The colors corresponds to the values of this function. And this function is obtained at every moment of time with very high frequency in time. And here, the left image, for example, corresponds to the time 180 milliseconds. And the next image, it's 190 milliseconds, so 10 milliseconds later. We have two functions, and we understand that this left function, it gradually changes, and we come to this right function, and so on. Every several milliseconds, we obtain a new function. So the idea of the method is to analyze these functions. So I repeat, we have a function, I call it f of x and y, of two space variables and of time t. So the method I will talk about today, and which is called optical flow method, is a method to analyze these functions. And that's all. So we can forget now about EEG data for a moment. We only know that we have a function of two space variable and of time, and we will analyze these functions. So it's a general method to analyze some data which is represented like that. So the first step in this analysis will be that to this function f, starting from this function, we will construct the vector field uv. What this means, uev, it's a vector on the plane with coordinates u and v. And this vector, of course, will depend on time. But for the fixed moment of time, we obtain this vector u and v everywhere inside our domain. So we obtain what is called vector field, plane vector field, and we will analyze this. Well, I will recall, not that we will analyze, because what I will talk about, it's very well known methods or results in the theory of dynamical systems. So I will recall some simple and well-known results from the theory of dynamical systems, which will allow us to make some conclusions about these vector fields. So the first step, we construct this vector field. The second step, we analyze this vector field. And after that, we recall that all that we done to study EEG data. So we'll return to this EEG and apply this method, and we'll see what it will give us. So this is the idea of my today's presentation. So let us start. Why optical flow? Because this method was first developed to analyze images from different areas, and this is why optical flow, but then it was applied in many different areas. So here's, well, schematically, maybe not very nice picture, but still I try to show some function of f of two space variable x and y and of time t. So let us consider the equation f of all z equals some constant a. If we consider this equation for time t, we solve this equation f of, some technical problems, f equals a for some moment t. So it is quite possible that we will obtain some curve on the plane where this function of two variables equals some constant a. If we consider the same equation a little bit later for time t plus delta t, again equal to the same constant a, we will obtain some other curve. So our curve moves on the plane, so for different moments of time, we obtain different curves, and we suppose, of course, that this function is sufficiently smooth, like continuous derivatives, all that. So we can reasonably assume that our curve moves in a continuous way. And then if we take a point at this curve, for example, as here, so sometime later, this point will move here. And if we start here, it will move here. So at each point of the curve, we obtain such a vector. And so we will have many vectors on the plane. And then if we take another value of A, we will obtain another curve, another vector, and so on. So for each moment of time, we obtain at each moment of space of plane, we obtain a vector. So we have many vectors on the plane, which cover the whole plane, and this is called vector field. Well, I hope this is clear, because this is very simple, and these are some basic notions. So the first step from the function f, we construct this vector field u, we call it u and v. If we do it formally mathematically, so then it can be written in this way. So we have this function f of x, y, t equals some constant, and we want to find the trajectory of this point. So we say that, in fact, this point on the plane depends, its coordinate depends on time t. So we have then here x of t, y of t. We differentiate this equation with respect to time. So what we obtain, so this derivative with respect to the first variable x prime, we call it u. Derivative with respect to second variable times y prime, we call it v, and derivative with respect to time. So like that, we have such equation. So what we have some given function. So should be, I should repeat to make it clear that f is a given function of x, y, and t. After this differentiation, we obtain such equation. U and v are unknowns. So f is given, u and v are unknowns, but we have only one equation written here and two unknowns. So we cannot uniquely solve this equation with respect to u and v. We want to find u and v, but we cannot do it in a unique way because we have only one equation. So what people do to avoid this uncertainty? So in fact, there are these two equations written here. Instead of one equation, we write two equations. So this expression here, written here, and here, it is the same expression, and it is exactly as it was before. You see here. So this is the same expression. So before, our equation was that this expression equals 0. Now, instead of writing this expression equals 0, we write some other equation. Delta here is Laplacian, so Laplace operator, meaning the sum of second derivatives with respect to u. Here, the same with respect to v. Some coefficients alpha here, and multiplied by f prime here, f prime here. So if alpha equals 0, we obtain exactly the same equation as before. But if alpha is small, we obtain an elliptic boundary value problem, because of course, it is considered in some bounded domain with some boundary conditions. It is called elliptic boundary value problem. And alpha here and this Laplace operator, it's a regularization. So for 0 alpha, we obtain the same equation, but for small alpha, the equations are different. This problem has now a unique solution. Well, maybe under some conditions, but in principle, this problem has a unique solution, u and v, and this unique solution, u and v, is close to the solution of this previous equation, because if alpha is small, so these terms are also small. This is why it's not exactly the same solution, the same equation as before, but in some sense, almost the same. So the solution of this equation will be close to the solution of this equation. But now the solution is unique. However, of course, you can also understand that we have some uncertainty here because, for example, this parameter alpha, its value is not well. We can take different values, and these different values, for each of them, we will obtain another solution. But if these values are small, we can reasonably assume that when alpha converges to 0, so our solution converges to something. So if alpha is small, we'll have the solution close to our limiting solution. In this sense, the value of alpha may be not very important. Anyway, so this is this method of optical flow. It's exactly that. So we solve this boundary value problem. We find u and v at each moment of space, so depending on x and on y, and then it depends also on c. So for every moment of time, we have this vector field u and v on the plane. So this is what I wrote here. So we have done the first step. We started from some given function f, and we obtained this vector field u and v, plane vector field. But it depends also on time. So our second step will be to introduce some tools to analyze these vector fields. Yes, this is a summary of what I'm talking about. And also it is, well, I will explain what I will present right now in analyzing these vector fields. So again, we start here with some functions here. Well, in fact, it's shown each data in some 2 consecutive moments of time. When we have these 2 functions, we construct this vector field as shown here, solving this boundary value problem. Then we will analyze we will analyze this vector field, and what means how we will analyze it, and what means optical flow patterns. So in fact, this vector field is, in fact, what I'm saying now, it is applicable for any plane vector field, not only plane, by the way. So this vector field can have stationary points. What means stationary points? These are points where u and v equal 0. These are called stationary points of the vector field. And when we determine the stationary point, we can analyze the types of the stationary point, as we know from the theory of dynamical systems, or for those of you who are more familiar with mathematical interpretation, we can consider it as ordinary differential equations, the stationary points, because ordinary differential equations produce this vector field. So we have 2 ordinary differential equations. They will give us similar vector fields. Then we can analyze stationary points and the types of the stationary points. What means types? So stationary points of this dynamical system can be different, and we know well, of course, that it can be, for example, nodes, saddles, and so on so far. And to determine the types of the stationary points, we need to take this matrix written here, A matrix A, so and V, these are our vector fields. So we take the derivative with respect to X and Y, and we analyze the eigenvalues of this matrix. So this is what I will briefly recall now, because we will need it for what follows. So again, we have our vector field u and v, functions which depend on these 2 variables. Stationary points of this vector field are the points x and y where u and v equal 0. So at the stationary points, we consider this matrix of partial derivatives, Jacobian, and we determine the eigenvalues of this matrix. And then depending on this eigenvalues, for example, if both eigenvalues are positive, then it is unstable node. if if they are complex conjugate with positive real parts, it's unstable focus, and so on. For negative eigenvalues, we have stable focus. Stable node. For complex conjugate with negative real parts, it's stable nodes. And of course, if one eigenvalue is negative and another one is positive, we have a saddle point. So of course, this the theory of dynamical systems, especially in 2 dimensions, in something which is very well known, very well developed. I don't know from what time, certainly from the time of Poincaré, maybe even before. And I will recall some very simple properties of such vector fields. For example, let us see what is shown here. There are 3 stationary points. This left stationary point is a node. You see all vectors converge here. It's a stable node. And this stationary point at the right is also a stable node. All trajectories converge here. So we have 2 stable nodes here. So if we have 2 stable nodes, necessarily, between them, there is a saddle point. Shown like here, because you see, we need to go here this way, here this way, but by continuity, these vectors come here this way. This is why here we have the saddle points. Of course, their position can be a little bit different, but the idea is always the same. If we have 2 stable nodes, there is somewhere a saddle point in between. Of course, it's not a precise mathematical formulation. All what I'm saying now can be done in a more rigorous way, but since this is very simple and we don't have time, of course, for all this mathematical details, so what I present is kind of an explanation. So the first property we should keep in mind is that if we have nodes, then there are saddles in between. We continue this analysis a little bit in more detail. So this is a stable node. We say that if it is a stable node, then both eigenvalues are negative. Let us call n the number of positive eigenvalues. So in this case, obviously, n equals 0. The same for this node, which is here. It is different for the saddle point, which is in between, because one eigenvalue is positive, another is negative, so the number of positive eigenvalues is 1. Next, we introduce what is called the index of the stationary point. It's very simple. The index of the stationary point is -1 to the power n. N is the number of positive eigenvalues. So the index is written here. -1 to the power 0 is 1. Here it's also 1. Here in between, -1 to the power 1, it's -1. So the index of stationary points for stable node is 1. For saddle is -1. We can determine, of course, it's for all other points. For example, if we take focus, either stable or unstable, but there are complex conjugate eigenvalues. For example, if you take unstable node, so there are 2 positive eigenvalues. So n equal 2. So we have -1 to the power 2. It gives again 1. So from this point of view, unstable node and stable node are similar because the indices are equal to each other, equal to 1. The next step in our construction, so we consider some domain, 2-dimensional domain. And inside this domain, there are several stationary points. So what we do, to each stationary point, we prescribe its index. For example, here, this is stable node. Stable node is 1, it's 1. Here it's a saddle, it's -1. So the next what we do, we take the sum of these numbers, and we call it gamma. Gamma equal the sum of these indices, the sum of these numbers. In other words, -1 to the power n for each stationary point. So this is all very simple. But behind the simplicity, there is a just huge and very important mathematical series. This number gamma, which we introduce here, it is called topological degree, or in other words, rotation of the vector field. It's the topological degree theory is one of the most important and beautiful mathematical theory, which is used, of course, not only for such simple problems, but for many other problems, including partial differential equations, integral equations, whatever we can imagine. And it allows us to prove existence of solutions, to study bifurcations of solutions, and so on. So here it's really the most simple example of this topological degree theory. And we can now apply this topological degree theory, and this theory tells us that if we consider now this vector field u and v, I recall it depends on t. T is time. So, but for us in this, from the point of view of this vector field, t is a parameter. So we consider our vector field dependent on this parameter t. We have our domain shown here, and we have some stationary points. And when we change t, the number of the stationary points can change. The number of the stationary points can change, but one of the most important results of this topological degree theory tells us that the topological degree, this gamma, is the same here and here. So the number of points can change, but gamma remains the same. So in the other words, well, in the mathematical terminology, we say that topological degree gamma is homotopy invariant. What means homotopy invariant? We have a continuous deformation of our dynamical system. This gamma does not change. This is called homotopy or topological invariant, homotopy invariant. This is very important. But there is one condition which should be satisfied. And this condition is that when we change t, parameter t, the stationary point cannot cross the boundary. This is a very important condition. So I repeat again now with this condition. If I start again. We change our parameter t. If during this change of parameter t, stationary points don't cross the boundary, then this gamma is constant. It doesn't change. So here we have 1 point. Here we have 3 points. Gamma is the same. So here, for example, there is one stable node. It is 1. Here, 2 stable nodes, 1 saddle. We take the sum of that. Gamma equals 1. We don't know how many points will be here when we change t. It can be, I don't know, 1 or 3 or 1,000, but the gamma will be the same. And this is very important. Of course, as I say again, there are many things behind. So what I present today is just really a very small part of the theory, and we use some results of the theory. So let us keep in mind this result that gamma remains the same. The next step from here, we say that if we take nodes, for each node, there are either 2 positive eigenvalues or 2 negative eigenvalues, but -1 to the power n is always 1. So the index of the stationary point is 1. So what is written here? -1, we have the sum -1 to the power n for all nodes we obtain ones. So 1 plus 1 plus 1 plus 1. For each node, we have 1. For each saddle, we have minus 1, minus 1, minus 1, minus 1. So the number of ones here, it is the same as the number of nodes. And the number of minus ones here is the same as the number of saddles. So gamma equals the number of nodes minus the number of saddles. And since we know now that gamma does not change, it says that the difference between the number of nodes and the number of saddles doesn't change. Each of them can change, but the difference remains constant in time. Under some conditions, I will not repeat it again. So since I see only Anastasia, and since it's an important point, Anastasia, confirm me, please, whether it is clear.
This is clear, but there was Yes, this is clear about gamma, which is stay the same at time, but there was some connection interruption. Could you please repeat what is the index for focus?
Okay, so let us return where here. So if there are connection interruption, as you say, so then
no, not for all.
No, interrupt me, and I will repeat, because
okay,
otherwise
in most cases the sound will start again from that point that it will stop. So it's just a few seconds, but not for the index of the focus.
Okay, I will repeat. So for each stationary point, we can determine this number -1 to the power n, where n is the number of positive eigenvalues of the corresponding matrix. Okay?
Any positive eigenvalues, not only real.
Real. Only real. If we have complex conjugate eigenvalues, as in the case of focus, n equals 0.
Yes, I understand. Thank you.
So for nodes and focuses, we have index equal 1. For stable node and unstable node, n is different, but -1 to the power n is the same.
Yes, I understand. Thank you. And one more point about the stationary points, which change the number in time. I thought that stationary points is for ordinary differential systems. This is the solution which does not change in time. So could you please comment how in time there can be more stationary points?
Well, unfortunately, I cannot write here, but anyway, let us take an ordinary differential system of equations. Du dt equals f of u. So now we say that this system depends on parameter. We call this parameter t. So we have f of u comma t. So this function changes.
Yes, I understand in this case. If we think about this like about the parameter, I can understand. Thank you.
Yes, we think about it as a parameter. The function changes. So we forget about this differential equations. We have just a function f of x, y, t. For each fixed t, we consider this equation f of x, y equals 0. We find stationary points. And then for another t, the function changes, the number of points can be different.
Yes, I understand now. Thank you.
So this very simple analysis gives us that the number of nodes, of course I simplify, but in these nodes we count stable nodes, unstable nodes, and focuses. The number of nodes minus the number of saddles is constant, meaning that when we change time, this difference does not change. So each of them can change. So this is what is written here. Number of nodes minus number of saddles equal constant. Under that condition, which is very important, that stationary point cannot cross the boundary. Well, it's another important condition, and the huge mathematical theory related to that, a priori estimates of solutions, existence of solutions, all that, we cannot discuss these questions today. I presented, I think, several times in our different seminars, but I will not discuss this today. So what are our conclusions? In fact, we have two conclusions. What we discussed right now, that nodes are separated by saddles, and the number of nodes minus the number of saddles is constant. Well, the next step would be, so what we say, we have this function f, we determine the vector field u and v, then we study the properties of this vector field, what we discussed now. Up to now, it was just some abstract construction. To make it specific, we should really, for some given functions f, we should determine these vector fields. So we should do that. And there are two ways to do it, either analytically or numerically. Analytically, but I recall that we need to solve a just elliptic boundary value problem, which is not obvious to do analytically. So in some simple cases or in some approximate cases, we can find an analytical solution. And I will not stop on that at all, because it's difficult to do it like during a seminar, moreover online. So what is missing here? It's analytical solution. Numerical solution we will discuss later. Instead of presenting this analytical solution, I will give one example. Well, I have several examples. I will stop only on one example. And this one example will be for what we call, and we discussed it last time when I presented this modeling of EEG data, we consider standing waves. What is standing waves? I showed here in this figure. So this horizontal axis is x, and we have such a function shown in blue like a sinus. Well, it's not exactly sinus, it's to the opposite side, not important. Now it depends on time. How it depends on time? It oscillates. So we multiply it by another sinus of time or cosinus, so it will oscillate. So you see this green line here, it's another moment of time, it changes a little bit. If we continue like that, it will grow here and will become like that here, positive here, and negative here, and so on so far. So standing waves, these are functions which have fixed zeros, 0 here, here, and here, and they oscillate like that as functions periodically as functions of time. These are stable standing waves in one dimension. But if we take it in two dimensions, you can easily imagine what I tried to draw here. Maybe maybe it's not very nice, but at least I hope that it is clear. It's kind of like surface like that, like Anastasia, I cannot express. Is it clear what it is in two dimensions? Like a surface, to compare with what, like a head?
For me, right? Yes, paraboloid.
Okay. Paraboloid. Okay, let it be paraboloid. Excellent. So this is our surface, which is like that. It's some moment of time. This is blue. Then at some next moment of time, it becomes a little bit less. It is green. And then so on, so far, because then at some moment it becomes 0, then it becomes negative, and then it oscillates like that. Let us compare this blue surface and green surface. What means compare? This is our function f of x and y and time t. So we write this equation f equals a. So this plane which I showed here, it's our constant A. So we solve our equation F equals A. If we do it for this blue surface, we will obtain this circle. It's how our plane intersect this, let us call it parabola. We obtain this circle. But the next moment of time, our paraboloid became a little bit less green. So our circle also becomes a little bit less. If we do now what we like geometrical interpretation, which we did in the beginning, so how these points move, how these points from the blue curve move to the points at the green curve, they move like it is shown with these arrows. So they move from outside to inside, right? So, and this, it exactly corresponds to this our stable node. This vector field, which is shown here, which moves from outside to inside, it is exactly what happens for stable nodes, right? Okay. If you do it in the opposite way, so if you go from green to blue, so the first one was our paraboloid decreases. Now, if our paraboloid increases, then we move in the opposite way from green to blue. Moves in the opposite way. We have, in this case, unstable node. Now, we have all these nodes, stable, unstable. In this, sometimes, well, in the theory of dynamical systems or in this optical flow methods and all that, they call them sinks and sources. So sink, so stable node when arrows are directed inside, they are called sink. And when arrows are directed outside unstable node, they call it sources. So we can use also this terminology, sink and source. So let us summarize. Yes, by the way, all this sink, source, and when it is focused, so they call it also spiral. So all that sinks, sources, spirals, this is exactly what is called optical flow patterns. So the title of my presentation was about optical flow patterns. So why optical flow? Because we introduced this vector field. Now we determine stationary points and their types, sink, source, spiral, or saddle. And this sink, source, spiral, saddle, they are called optical flow patterns. So what we do now, we determined some properties of this optical flow patterns, and these properties are summarized here. Let me repeat. When we have maximum and minimum of these functions f, so they give us all this maximum and minimum, they give us stable or unstable nodes, as we saw. In the other was sources or sinks. Moreover, we see that these sources and sinks are located at the same places because here this is the minimum, it grows, but then it becomes a maximum, it decays. So, but this minimum and maximum, they are located at the same points in space. So sources and sinks are located at the same places, and we discussed before. They are located at the same places, and they change each other. So the same point for some moments of time it is a source, for some other moment of time it is a sink. It depends whether it grows or decays. The same point can be either source or sink. Half period it is a source, another half period it is a sink. again, when it goes down, it is a source. When it goes up, it is a sink. But since it is periodic in time, the same point goes either down or up periodically. So it is the same point, but sometimes half period it is a source, some half period it is a sink. So again, so we have this maximum and minimum sources and sinks located at the same point but changing other. Well, I skip about the frequency to make it simple. So saddles are located between sources and sinks, and the number of saddles minus the number of sources and sinks in time. So these are our conclusions about this, what we call now optical flow patterns. To obtain these conclusions, we did some assumptions. We consider standing waves. We did some other assumptions. So these are not general results like mathematical theorems, but it's a modeling. It's under some conditions and under some approximations, we obtain these results. Now we will check these results with numerical simulations, whether it works or not. And I will show two kinds of numerical results. The first one is for this software. I presented it last time. So it calculates electric field in the human brain, but it's not a real EEG data. It's these are numerical simulations which show how this electric potential in the human brain changes if we introduce 3 stimulating electrodes. And okay, I thought that normally it should be a video. It looks like it doesn't work. Yeah, it works. So this is how it represents. So we do these numerical simulations on the real brain. We project it on the circle, and you see how this function change. The scales correspond to different values of this two-dimensional function. We discussed all that before, and you see these black lines. These are level lines of this function. They change in time, and this change of this function in time produces our vector field and all these patterns. Then also I discussed last time that we can have different situations. We can have standing waves shown here, but we can have also some other regimes, and this depends on the phases and frequencies. So of our sources of these stimulating electrodes. If they have equal frequencies and phases, we have standing waves. If phases or frequencies are different, so this is a little bit complex. These are not exactly standing waves. Now, what we see here, we have this. We do exactly what I presented now. We have this function f, x, y, and z. We construct this u and v. We apply all that, and we find these patterns: sources, sinks, and saddles. So let us verify our conclusions. So the first conclusion was that sources and sinks are located at the same places. So it is shown here. So this is time, for example, in this figure, this is time, and this is one coordinate. So if so green points are sinks, red points are sources. So you see that they are exactly at the same, the coordinate exactly the same, and they change periodically in time. So the first conclusion is exactly verified. So they are located at the same places, and they change each other in time. Second conclusion is that saddles are between sources and sinks, and saddles here are these crosses, gray crosses, and we see they are exactly in between. So this is another coordinate, and this is projection on two coordinates. And we see, so these two red dots, in fact, these are red and green at the same time. This is exactly positions, these red dots, exactly positions of our sources and sinks here. And these gray crosses are positions of saddles, and we see that indeed all these properties are satisfied. And another, our conclusion was about the number of saddles and sources and sinks. Again, here this conclusion is exactly satisfied. The number are constant in time, and in fact here in the simulation there are 17 sinks, 18 sources, and 38 saddles. So when we consider standing waves, our conclusions are exactly satisfied. If we consider more complex behavior, these are not exactly standing waves, but phases of frequencies can be different. But so our analytical conclusion was done for the standing waves, and here we verify that in fact, indeed, these conclusions are still verified. It's a little bit not so ordered as for standing waves. You see that positions can be a little bit different, but however, these conclusions remain true, that sources and sinks are located in the same places, alternate each other in time, saddles are located between them, and the number of saddles and other patterns correlate. So this is for numerical simulations. And now we return to electroencephalography. So I will not repeat all that. We have, these are experiments, what is called image naming experiments. So the person, so there is a screen between the person, there is an object on the screen, so the person pronounces the what names the object, and all that is registered with electroencephalography. And then we have this data, and so what we have here. So this, of course, it is an example because there are huge amount of there's a huge amount of data like that. I give you only a couple of examples. So here we take one subject. It's called S15, subject number 15, and we do all this what I presented before, and we determine the position of sinks. And the position of sinks, well, it's the number is shown with color, but okay, let us make it more simple. So we can say that the position of sinks, these are these bright spots here. This is the position of sinks. If we consider now the position of sources, we see here exactly the same positions, exactly the same distribution as here. If you take the position of spirals, we have the same as before. For the position of, it is called spirals in, it's a stable focus, spirals out, unstable focus, a little bit different. If you take now the position of saddles, shown here in the last image, here we said it should be in between. It is difficult to verify it like that. In fact, this is true, but it can be difficult to verify it in this image. I will return to this later. This is for beta frequency range. If we take for alpha frequency range, so these distributions are very similar. This is what we say, that these distributions do not depend on the frequency. So more detailed statistical analysis, because it was done in a quite extensive statistical analysis of this data, and I skip all. I will show only this left figure. What is shown here? It's a position of. Here, if you take the left column, it's the position of spirals, sinks, and sources. So let us forget about, for example, spirals. Let us take sink, it's green, source is red. So our conclusion was that they should be at the same places. Now this two big circles here, this big green circle and big red circle. If these circles are completely coincide, this means that they have exactly the same position. If they are completely separated, then this means that they have completely different positions. So the overlapping of these circles show how much these sinks and sources overlap. So we see that they indeed overlap. Unfortunately, I didn't give the number here, but they overlap. I don't remember, about 70 or 80%. So we can say that yes, indeed, the conclusion is correct. Sinks and sources are mostly overlap. These are green and red circles, and gray circle is spiral. This is also true for spirals. So all of them mostly overlap according to our previous result. If we take now saddles, should be between sinks and sources, so they should not overlap, right? So gray, it's this big gray circle, it's saddle, and this sink and sources. We see that gray circle basically does not overlap with these colored circles. So our conclusion is correct that indeed saddles don't overlap with sink and sources. They are located between them. And since my time is almost over, so I will finish with this figure, which shows, you remember our another conclusion was about the number of saddles and whatever sink sources. Here, this figure summarizes all results for all subjects. There were many subjects, and for each of the subjects, there were different frequencies, so on, so far. So if we summarize, and for each subject, there were many, they call it trials. So each word, each image and word, it's one trial. So for each of them, it was about 100 trials. So all this data put together. So we see that red line here shows the difference between the number of saddles and the number of others, and we see that this red curve is more or less constant with small oscillations, of course, but basically it is constant. So this confirms our conclusion that the difference between the number of saddles and the others remains constant. So I will stop on that, and I will just make some conclusions and some discussion about all that. So this method allows us to study this, what they call complex patterns, meaning the sources, sinks, spirals, saddles, and to make conclusions about location of these patterns and about their number, what we discussed. What I write also here, these complex patterns and plane waves. Unfortunately, I did not have time to discuss about plane waves, so I will tell it very shortly now. If we do this analysis, I presented this analysis of these patterns for different functions. If we do this analysis for waves, so we can conclude that in fact there are no patterns for waves. Again, When we take standing waves, we obtain all the sources, sinks, settles. If we do the same analysis not for standing waves, but for traveling waves, we obtain that there are no patterns, no sources, sinks, and settles. It means that patterns and waves, they are not compatible. They do not exist at the same time. Again, I don't have time to discuss that, but this conclusion was confirmed in the experimental results. So these patterns and waves, they do not, usually they do not coexist. We obtained that in this analysis, and there are experimental results which confirm that. Again, location and number we discussed. What means amplitude and phase? I skip that. Then about positions of these patterns. So we say that there are some spatial location where these patterns are located. We don't know why they are located in some particular places. Like, for example, here, you see the spots here. In fact, it's a projection of the scalp. It's not just, it's really how these patterns are located on the scalp. Why they form such a structure? Why they are located in a particular way and not in some other, we don't know. And for different people, the structure is different. All these conclusions are the same for all people, but location of this are different for different people. And we don't know why. So it may be certainly related to some anatomical structures in the brain. And these anatomical structures can be different for different people, but we don't know, in fact. And also the last point, which I will not could not discuss today and will not discuss now, just mention that all this is done for this experiment, picture naming experiment shown here. So how all these patterns are related to this picture naming experiment, because in this picture naming experiment, there are different stages. The first one, for example, is image recognition. When we see an object on the screen, our brain recognizes this image. It's the first step. Then there are several intermediate steps, and finally we pronounce the word. So all of these stages are very complex, and there are really many things happening in the brain. So how these patterns which we analyze, how they depend on these different stages in picture naming task. This is a very complex question. There are some results about that, but these results are not conclusive, not definitive, and I will not discuss them today. So I stop on that. The final summary is that optical flow method allows us to determine these patterns and to analyze some properties of these patterns. Thank you for your attention.
Thank you very much. May I have one question?
Yes, please, of course.
It's about the conclusion that the standing waves and traveling waves cannot coexist in electroencephalography patterns, as I understand. So could we conclude that the brain, while recognizing images, works like produces just standing waves, and there is no traveling waves in this case? And could there be traveling waves in different cases?
Now, all that is very complex, and in fact, it is largely discussed in the literature, both in the biological literature and modeling literature, and the conclusions, in fact, are not known. So there are some observations like that. For example, that what we say that the waves and the patterns do not exist at the same time. There are many studies about these waves, but all that is very preliminary. and we don't have definitive conclusions about the role of these waves and the role of these patterns. If, well, maybe some other time I will give a seminar about waves in electroencephalography, because, and not only in electroencephalography, but in more general in brain activity. It's not only electroencephalography, because there are also other methods like ECOG, for example, and other methods, or magneto, how it is called?
Right.
No, well, it is, yes, it's called, well, kind of MRI, but not exactly. There are different names.
Brain, yes.
Yes, so there are different methods to study this brain activity, and these different methods also allow to study these patterns and waves. So there are quite many results, but we don't really understand the functional role of these waves. We need to discuss that. I think that maybe we'll have some time later to discuss that about the waves. It's very interesting, in fact. Yes, but at the moment not very clear.
Mm-hmm. And on the data, the peaks, they produce the sources of the electric potential. There are some sources in the brain, or it comes from electrodes on these pictures which you show.
I showed you two kinds of results. Results numerical simulations of the brain, and these results are obtained for stimulating electrodes.
Mm-hmm.
It may be not necessarily numerical simulations. This is what really they do, and even in our group we did that. So there are stimulating electrodes put on the scalp, and then the signal registered around, and you can study this distribution of the signal, in particular these patterns. So what I showed, it was simulations. It was not real data, but simulated data on the realistic geometry. There are this stimulating electrodes, and then electric potential is measured, and then all that what I showed you about all these patterns was done for this data. It's the first one. And the second one, it was a real data obtained from people without electric stimulation. It's their own brain produces electricity, electric potential. As we discussed during the previous seminar, there are brain sources of not in the same, well, the word sources is very unfortunate because it is used in many different meanings. So sources in the sense of previous seminar, sources of electric potential, not sources as
yes, I remember.
So in our brain, there are sources of electric potential. They produce these electric oscillations, and these electric oscillations are projected on the scalp and registered by the electrodes. When we register these oscillations and we apply this optical flow method, we obtain all these patterns on the scalp. But we don't know how the patterns on the scalp, whether they are related to the sources which are inside. We just don't know. We can imagine that they somehow correlate, but we don't know.
Okay, I understand. Thank you.
Well, if no other questions, then I think that we can stop for today. Thank you for listening and discussion, and have a good day. Bye.
Thank you very much. Goodbye.
Thank you. Goodbye.
Goodbye.
Goodbye.